In this video, we're going to look at the last of our 5 important lemmas. To start with, again, I want to go back through the lemmas that we have already proven. To start with, lemma 1 said that if we have a group and A was any element of G, if we had A triangled with itself winds up being equal to A, then A wound up being the right identity element of the group. The second lemma said that right inverses are two-sided inverses. In other words, if I know that A triangled with A hat is equal to ER, then I also know that A hat triangled with A is equal to ER. Our third lemma said that the right identity promised in axiom 3 is actually a two-sided identity element. In other words, we know for all elements inside the group G, A triangled with ER is equal to A, but we now also know that ER triangled with A is equal to A. The fourth lemma says that ER is the only identity element inside the group. And now we're ready to state lemma 5. So let's state lemma 5. Lemma 5 says this: we're going to let G under triangle be a group. Let's let A be any element inside that group. Then the right inverse of A is unique. Now, before proving this, again, I want to think about what this actually says and how to go about proving it. So saying that the right inverse of A is unique means that A only has one inverse element, because we already know that every right inverse of it is A is going to be a left inverse of A. So to show this, what we're going to do is we're going to assume that A triangled with A hat is equal to ER, and we're also going to assume that A triangled with B is equal to ER, and we need to show that A hat and B are one and the same element. Because if I can do that, then there is only one right inverse, and that right inverse will actually be a two-sided inverse. Well, how am I going to do this? Well, let's think about what we know and see what we can string together. So here's what we know. We know that A triangled with A hat is equal to ER, and that's by axiom 4. We also are assuming that A triangled with B is equal to ER. That is our main hypothesis, that we have another potential right identity element. We also know about lemma 2. Lemma 2 says A hat triangled with A is going to be equal to R. And we also know lemma 3, which says ER triangled with anything, and I'm going to say this as a G, is going to be G for all G inside group G. So in particular, we're going to know that ER triangled with A is equal to A. We know that ER triangled with A hat is equal to A hat. And we know that ER triangled with B is equal to B. All of these are from lemma 3. Now what I want to do is I want to think very hard about these two things here. I can put them together to get an equation that I can manipulate. So let's look at that. We know that A triangled with A hat is equal to ER, and we know that that's also A triangled with B. That is our main hypothesis. So that's obviously going to tell us that A triangled with A hat is equal to A triangled with B. And what I can do at this stage is I can pre-multiply this particular equation by A hat. So I choose to pre-multiply by A hat to get A hat triangled with A hat is going to have to be equal to A hat triangled with A triangled with B. Now we are in a group, and consequently we can move those parentheses around, and I'm going to move the parentheses around and rewrite this equation as parenthesis A hat triangled with A hat, and over here I'm going to write this as A hat triangled with A triangled with B. And this is by associativity, or in other words, axiom 2. But now what I want to do is I want to realize that at this point lemma 2 kicks in, and lemma 2 says this is E and this is E. So that equation now becomes ER triangled with A hat is equal to ER triangled with B. That is by lemma 2. Of course, our right identity element is also a left identity element by lemma 3, and so this particular equation can now be rewritten as A hat is equal to B by lemma 3. And we wrote all of these things down on the previous page. And you can go back and look at the earlier in the video to see that these things do indeed follow. And this completes the formal proof. Now, I do have some comments to say about what we've actually done. We have shown that A inside G has a unique right inverse. But that right inverse is actually a two-sided inverse by lemma 2. And consequently, what we now have is that A has a unique two-sided inverse. And it is traditional to define or use the notation A to the negative 1 to denote the unique two-sided inverse of the element A inside our group G.